Good morning, everybody. So today should be a relatively short day. We don't have a whole lot of things left to cover. Just want to remind you on the syllabus real quick. Pull that up. So, okay, we've got our class today. Remember, your activity participation 2 should be due today. If you haven't done that yet, go ahead and get that in. Next week we have Thanksgiving, so we won't be in class during the Thanksgiving break on Wednesday, so there's no class. And then we come back and finish up with one last class on November the 29th, and so that will be our final day. I just want to remind everybody there is no final exam in this class, so you do not need to find where the final exam is in relation to the schedule. Does everybody know how to find their schedule for their final exam? Okay. So you can find that on the registrar's website. You can go to the registrar's website and you can look up the final exam schedule. Your final exams are not scheduled for your normal class time. Now, your instructors in your other classes may have said something about your last class being your final exam. That happens sometimes. Be sure you understand when your final exam time is. Okay, some instructors are very persnickety about final exam time. There are some on campus who will, at the start of the exam time, they will shut the door and not let anybody else in. So it's important that you get to the final exam time on time and take your exams really very seriously, of course, because that's going to be your last opportunity to get whatever it is that you've set for yourself this semester. Now, everybody has their own final exam policies, so make sure you understand in your different syllabi what that policy is. Some folks, myself included, when I give in a regular class giving an exam, the final exam could be replace your entire course grade. So if you took my organic class, for example, and you got an A on the final exam, but your overall grade was a C, I'd give you the A. Okay, some faculty do that, some faculty do not. So you'll need to know what your final exam policies are in your syllabi for your various classes. So keep all that in mind. Any questions about that? Okay. Once final exams are over, unless you've got an arrangement with your faculty member to get an I and then come back and do something, I mean, that happens sometimes. I mean, that's it. So just want you all to be aware of that. So they're called final exams for a reason. All right. Dr. Kessel was not able to attend this morning, but he sent a short video about his research. It's very short. Some of you have probably already seen it, but I'll go ahead and play it in here, and we'll talk about it in just a minute.
Just a few decades ago, the HIV epidemic became widespread worldwide with a very short life expectancy.
In the 80s and the 90s, when the first case appeared, people were dying and we didn't have any treatment to save them.
Decades later, treatments evolved, allowing patients options to treat the symptoms of AIDS with a so-called drug cocktail involving a combination of medicines. But now doctors are finding it tougher to control the progression of the disease because of the ever-changing properties of HIV.
So we need to stay ahead and design new strategy and new drug to have drugs that are ready for when the virus becomes resistant to the current drugs.
Work to study protein interactions of the virus is currently taking place here in this lab on the campus of the University of Southern Mississippi.
We try to design drugs that can interfere with this interaction and prevent the virus replication.
Researchers are partnering with biochemists at Southern Miss. That collaboration can often be the key to achieving breakthrough discoveries.
That's why a lot of people are trying to solve problems from different angles, and collaborating is one way to achieve that. In order to get different angles and they get different ideas and merge them together in order to solve one problem.
And ultimately improve the quality of life for patients.
So being able to design new drugs that can extend people's life is very rewarding.
From the University of Southern Mississippi, I'm Layla Esser.
All right, so what do you all take from that? What do we take from that short video?
That chemists constantly try to combat HIV, even though it's constantly involved in high
Okay, yeah, that's true. Anything else?
I just find it interesting that we do research like that on campus.
Why does that surprise you?
It doesn't surprise me, it's just, I didn't really think about HIV being one of the things that this campus focuses on, but it seems to be a lot of the researchers.
Uh-huh. Anybody know why we might be focusing on that in Mississippi?
It's, I wouldn't say rampant, but it's a pretty common thing in Mississippi.
It's true. In the Deep South, HIV actually does run, I mean, some people would say the word rampant. It does have, if you look at a heat map, which kind of shows incidents per like 100, like per 1,000 people or something like that. The Deep South, Mississippi, Southern Alabama, over into the Delta, Louisiana, HIV rates per, whatever it is, I think it's 1,000 people or 100,000 people, something like that. It's actually quite high in the South. And so having researchers come here to actually study this is kind of an important thing for our region, right? And so back in the 80s when I was a teenager, long before any of you were born, it was a death sentence. I mean, when you heard that somebody had contracted HIV, you knew that they probably didn't have long to live. That is no longer the case. I mean, we have drugs now that can allow people to live relatively, I mean, I would actually go as far as to say very normal lives and take treatments. You all may have seen things on TV these days, ads about drugs that actually can bring the virus level so low that it's undetectable. That's pretty impressive. I remember back in the late 80s, early 90s when people said, this will be a drug we cannot conquer. Scientists were saying that. This is a drug that we cannot conquer, or a disease that we cannot conquer with drugs. Through research and better understanding of the modes of action, differences in human behavior that were trying to be touted, we were able to bring it somewhat under control, and we're at a point now where we can actually treat people effectively, and they can expect to live, a normal lifespan. And so I think that's an impressive record for science. Do you think it's only biochemists that are involved in this type of research? Who else do you think are involved? How about here? I heard something. Geneticists, yeah, so knowing the gene things that go on with viruses, that's important. What else? Immunologists. Somebody, at least two people came and talked to you this semester that are involved with the work that Dr. Kessel does. Does anybody remember who they were? Dr. Donahue and Dr. Pigza. Dr. Pigza may not have talked a lot about the HIV piece, but they both have collaborations with Dr. Kessel. One of the things that he did not mention in his video is that he makes no drugs. You saw the little robot doing its thing? That's what he does. He does the assay, the HIV assay, to try to find inhibitors, and I forget what the enzyme is that they try to inhibit. It's not important for this talk. And so he's got that hammer, And Dr. Donahue and them have the hammer of being able to make molecules. These are small organic molecules that can bind into that. And so they've worked for quite some time. Now, of course, Dr. Kessel works with other people all across the nation that also make inhibitors. It's not just Dr. Donahue and Dr. Pigza. But I think it's really important to note that people that are on this campus just across the street from one another are collaborating. And so if this is something that interests you and you're interested in it on the biochemistry side, you might want to go talk to Dr. Kessel about rotating in his lab or performing research in his lab. But on the other hand, you might be interested in, and you're thinking, I really don't want to do the biochemistry part. I want to do the organic synthesis part. I want to make the molecules that might be druggable. You might want to go talk with Dr. Donahue. And in fact, those two labs quite frequently have joint meetings where they're talking about the research together. It truly is a collaborative effort. So just to keep that in mind as you might think about research opportunities going forward. All right. I asked you to read this about the skeptical chemist. What do you think I asked you to read something about the skeptical chemist? What does it mean to be skeptical?
Question.
To question? Yeah. How many of you in here are skeptical? Yeah, I'm skeptical. People tell me stuff all the time. Most of it's baloney, right? You watch stuff on YouTube, most of it's baloney. You watch stuff on TikTok, all of it's baloney, right? Well, not all of it. But I mean, a good amount of it is baloney, right? I mean, people will buy into. It's easy to buy into baloney, right? For some reason that I don't understand. And it's very, very important to be skeptical, right? Very, very important to be skeptical. So, the question, right? So where does that come into play? What would this idea of the skeptical chemist kind of been the starting point for? Scientific method, right? We've talked about that this semester, right? So let's review that again. And I keep going over it and over it with you all because it is the thing. No matter what major you decide you may not decide to be a chemistry major. You may change your major. You may change your major to art, but you still need to be able to think like a scientist. It's why it's in the GEC. Okay? You have to have science because you need to have this ability. So what are kind of the steps of the scientific method? Observation, right? We make an observation about something. What else? And we did that the other day with the little boxes, right? We were making observations. Hypothesis. Hypothesis is the central part of the scientific method. What is a hypothesis? Okay, it is a guess. I would add a few more adjectives to that, right? But what might we add to that? That's a very good start, though. It's a very educated guess, right? So we're not just guessing out of the wild blue yonder. We have a body of knowledge that we know. We go to the literature. We start to think about what have other people observed, what have they found, right? And so that's not quite what I'm looking at here. So let's make an educated guess based on what I know, what I've observed. We make an educated guess. What's the most important part of a hypothesis? I can make all kinds of guesses, right? But what's the central tenet of a hypothesis? What must it be? It is a question.
A prediction of what will happen.
A prediction of what will happen.
Is it testable?
It has to be testable. And testable in a way that does what? It has to be disprovable. That's the very important piece. And that is one of the pieces that separate the physical and natural sciences, chemistry, biology, physics, geology, from what we call the pseudosciences. And I'm not going to pick on any disciplines today. But there are disciplines that will talk about doing things scientifically, but they always look for things that prove their point. That's not scientific. When you develop a test to test your hypothesis, that test must be able to disprove the hypothesis. So does that mean that we can ever really and truly prove a hypothesis? No. It's possible that you could come up with a test on something that I've said, this hypothesis looks to be true, and I just haven't thought about it yet. And then we test with your test and, whoop, no, it's not true anymore, right? But what happens as a hypothesis becomes more and more accepted? Eventually we start to say it's what? A theory. We start to say it's true. We start to really believe it. And then if we figure out that, you know, almost everybody believes this and nobody's been able to find a test, then it might actually become a law, right? So there are laws of nature. Anybody know what, anybody give me an example of a law? Newton's laws. Coulomb's law. The law of conservation of matter. You probably learned about that, right? Although in nuclear stuff, that law doesn't hold, right? But under normal chemical reactions, it holds, right? We don't create or destroy matter in typical chemistry settings, right? So I really want you all to be, regardless of whether you stay chemist, biochemist, if you go to another science, if you go to arts, I want you to leave the university when you graduate with a skeptical mind. And that doesn't mean you're negative all the time. Some people say, oh, if you're skeptical all the time, you're negative all the time. I'm like, no. There's a lot of things that we want to believe, but you should be skeptical about it, right? You should always be skeptical about what people are telling you, even what nature's telling you, right? So it can be quite different. Anything else about the skeptical chemist? Anything anybody took from that? Okay. Acids and bases. Why would I pick for you to read about acids and bases, do you think? What's so important about acids and bases?
It's a basis, or it's like a base for a lot of reactions in chemistry.
That's right. 99%, in my estimation, of all chemistry, and certainly most of all biochemistry, can be broken down into an understanding of acids and bases. Okay? What do you know about acids and bases? In general, I'm not asking for specific theories yet. What do you know about acids and bases? In your everyday life, what do you know about acids and bases?
Just that acids and bases, their pHs are differing.
Okay, so differing pHs, right? What's a typical pH for an acid?
7.
The 7 would be water neutral, right? Okay. Anything below 7 would be a acid. Anything above 7 would be a base. Yeah. So that we're starting to, you kind of got the general chemistry concept of acids and bases there, and you all come into contact with acids and bases every day. Give me some examples of acids that you come into contact with.
Soda.
Pardon?
Soda.
Oh, yes, soda. Sprite. Lemons. Notice what you all just described. You've all described foodstuffs, right? Most foodstuffs are slightly acidic, if not acidic, right? How many people like pasta with tomato sauce? Tomato sauce is not basic, it's acidic, right? What was that?
So I know that gives me heartburn.
It gives you heartburn, yeah, yeah. But sometimes we eat it anyway, right? Because it's good. So we do that. What about bases? What do you all come into contact that might be bases? Pardon? Baking soda. Okay, yeah. Cleaning supplies. Yeah, it turns out that almost all of your cleaning supplies are basic, right? You think about Windex, it's ammonia and water, right? It's got that ammonia smell to it. It's a base. If you took the pH of it, it would turn the litmus paper blue, right? And so we come into contact with acids and bases every day. What happens when acids and bases come into contact with each other? Yeah, they undergo a process we call neutralization. What does that mean?
They get to the pH 7.
Okay, yeah, you're both right, yeah. So if we think about a strong acid and a strong base, they would react to form something that's neutral, right? Not all acid and base reactions ultimately give neutral things. What else about acids and bases do we know? Some of you may have learned an acid and a base gives a, okay, so a proton, H plus is an acid, okay? What else? So anyway, I was saying an acid and a base reacts to give what? Water, typically, and a salt. You all probably learned in high school or maybe in gen chem that an acid and a base reacts to give a salt plus water. Okay, and that's true at the general chemistry level. There are other acids and base reactions that go on. When you all get to organic, if you're not in organic now, you will learn that almost everything can be broken down into acid-base reactions. Using what theory of acids and bases? How many theories do we have? We have 3 basic theories of acids and bases. Anybody know what they are? Bronsted-Lowry, Arrhenius, and Lewis. That's right. And from my viewpoint, we teach you Arrhenius theory and we teach you Bronsted-Lowry theory from a historical perspective, because Lewis theory explains everything. Okay? Does anybody know what the Arrhenius theory was? Okay, yeah, so anything that was dissolved in water and made hydronium, H3O plus, or a proton, was considered to be an acid. And anything that was dissolved in water and gave hydroxide was considered to be a base, right? And that works. Then we had, what's the other theory? So that was the Arrhenius theory. Okay, let's talk about Lewis last. Bronsted-Lowry. And what did Bronsted and Lowry say? That's Lewis. Yeah, so it's about, did you donate a proton or did you accept a proton? If you accept a proton, you're a base. If you donate a proton, you're an acid. Kind of a expansion on the Bronsted-Lowry theory, or the Arrhenius theory, excuse me. And then finally, for all practical purposes, we have the Lewis theory. Okay? Did I tell you all the story about Lewis? No. All right, let's think about your gen, if you're in gen chem, how many times have you heard the word Lewis? A lot, right? So we know about Lewis acids and bases, and what else do we typically think of with Lewis? Structures, and you all hate those, right? Drawing the structures, right? Lewis is probably one of the most influential chemists, in my opinion, of the 20th century, and he did not win a Nobel Prize. He, in my opinion, should have won 2 Nobel Prizes. He should have won a Nobel Prize for his acid-base theory, and he should have won a Nobel Prize for his structural theories, okay? Because structure is so important, right? Anybody want to take a guess as to why he didn't win a Nobel Prize? Competition. Most of his colleagues thought he was an ass. I'll just be honest with you, okay? And so I don't want you all to think that all good things get rewarded, because that's just not how the world works. People actually make judgments, okay? I think he should have won at least 1 Nobel Prize. I think we could have argued 2, given the fact that everybody that starts off in general chemistry learns that person's name more than any other name out there. You've heard other names, but in each chapter that you're learning about in Gen Chem, you've probably heard the name Lewis come up at least once, okay? And so, very influential on how we thought about things. And prior to thinking about Lewis acids and Lewis bases, we were really had this hodgepodge of understandings of how the world worked chemically. Lewis theory all of a sudden brought it into focus as life, the world, everything is nothing more than a series of acid and base reactions, okay? And so I want you to understand that this is the most important concept as you study chemistry. When you get to organic, you're going to see things like this. You don't have to worry about it right now, but you're going to see reactions that might look something like this, and people push arrows. right? And you can break this whole, what we call mechanism down into nothing more than a series of acid and bases. This is a base, this is an acid. Okay? You'll learn that. When you get into biochemistry, they're going to talk to you about a lot of stuff. And if you can break it down into a series of acid and base reactions, you will have a true understanding of it. Otherwise, all you're doing is memorizing. Okay? But if you can break everything down into a series of acid and base reactions, you will truly be able to understand chemistry. And one of the things that I tell my students when I'm teaching a regular chemistry class is that when you're always trying to figure out what's going to happen, find the acid and find the base. And once you find the acid and you find the base, you can usually take reasonable steps to figure out what the product is going to be of that reaction. Okay? DNA has its structure because of acid-base reactions or interactions. Right? Hydrogen bonding is a series of acids and base type reactions. So this is the most important concept. Okay? How many of you are in 107 right now? Chemistry 107. So a couple of you, you're talking about acids and bases a lot right now. Make sure you leave this semester with a good understanding of that. The kinetic stuff, the mathematics of all of it, while important, will not serve you as well as having a good fundamental understanding of acids and bases. Okay? I can give you all a problem where you all have to solve and you will remember an equation and you'll give me a number and you won't really know intuitively whether that number is right or not. You'll just say, that's what the calculator told me. Right? But you need to be able to do that and then look at that number and go, does that make any sense? You need to be able to do that, right? I've seen students in the Gen Chem labs that have subtracted two masses and got a negative number and thought that that was correct. Why is that not correct? You can't have negative mass, right? Actually, we do have antimatter, but that's kind of a special case, right? But you don't have any of that working in the lab, right? You just don't. You can create some of that in the physics world, but you can't really create that here, okay? So, the point being, just because you remember an equation, just because you remember how to calculate something, doesn't mean you truly understand it. You need to understand. I can look at a reaction and I can go, that's a strong acid, that's a strong base, and it's producing a weak acid, weak base. I know immediately that the equilibrium is going to lie to the right. Do I know the exact number? No. Do I need to know it 99% of the time? No. I don't need to know the exact number. Right? But I have seen PhD scientists that have calculated a number and you look at it and you go, that just doesn't make any sense whatsoever. I've been in thesis defenses with people that were getting ready to get their PhD, and I'd go, you're taking a weak acid and a weak base and you're making a strong acid and a strong base. That's not how nature works. Oh, yeah. It's wrong. Well, how do you know it's wrong? Because I know the laws of nature. I know that that has to be there. I don't have to calculate anything. I know that that has to be wrong, right? Or you're not taking something else into account that you know. So you need to get what we call chemical common sense. And that's not going to come to you naturally. That's not going to come to you quickly. But it will come to you as you think about all of the courses that you take in each and every one of your courses. If you think about most of what we're talking about in terms of acids and bases, you will get that common sense. Okay? All right. Last thing for today. How many people have seen emails come to you all or in Canvas about course evaluations? Am I seeing some nods? Yeah. What is so important about course evaluations? Feedback. Yeah, it's your opportunity to provide feedback on the course. What do you all think about course evaluations? I want to know your opinions. You think it's a good thing? Okay. What else? What other opinions do we have?
I don't know. I think it's a little bit useless from my experience.
You think it's useless from your experience. What? Tell me why you think it's useless, and what was your experience?
I mean, right now I don't have like like a very good professor at like a course that I'm taking, and like kind of everybody agrees like on my class. And then we think about, maybe we can do something like to give feedback, but like it's not gonna change anything. Like, professor's still going to do the same over and over again, so I don't think it matters that much whatever we say in there.
Okay. Is that a legitimate point? It's a very legitimate point, right? That's how you feel about it, right?
But I've also had plenty of professors who take our feedback and change it in the middle of the semester to help. Like my sociology teacher, we made a complaint and she fixed it the next day.
But that took you all that wasn't at the end of the semester, right? That was
No.
getting feedback in interim, right?
She asked for feedback like every couple of weeks
Okay.
on things that she.
That's good. That's good. Good instructors typically do ask for feedback, or at least read the room and try to figure out what's going on, right? So I would argue that your experience and your feelings about course evaluations are probably in the majority. Most students feel that way. And I know that because my daughter's here and I have to listen to her about her feelings about course evaluation. But what I want to tell you is that course evaluations are your say. It is not your way. Right? Everybody in a democratic kind of system, it's trying to be democratic in the education system. We want student feedback. And just because you have your say doesn't mean you have your way, right? Every faculty member has their own teaching style. But what you have to hold on to a little bit is that there are faculty out there who will take the feedback as a whole and make changes. I do that. I know a lot of faculty members do that. So what I want you to know is that even though you might have this feeling of, well, it's not going to help me, it's at the end of the semester, remember that some of the improvements that you've experienced were because of feedback that others have gave. So it's your way of paying it forward to the next set of students. So you might be in a class right now and you're thinking, man, I just really can't get into what this teacher's doing. But you might want to think about what it might have been like 3 or 4 semesters ago. You might actually have the improved version, okay? And faculty, we are learning all the time. We have not. I had a little bit of training in how to be a teacher, a little bit of training. Most of us have 0 training in how to be a teacher. We're hired here to do research and do that kind of thing, and then we teach kind of on the side, so to speak. I'm not saying it's right, I'm just saying it's the way it is, okay? And if you want to have a say in terms of how things will improve in the future, please fill out your course evaluations, okay? I know it can be painful, I know it can seem redundant, and many of you will go through and just answer the questions. But there are those text boxes where you need to put commentary, okay? It's open, you can say whatever you want, but you need to say it in a way in where it's going to be effective. What do I mean by that?
Just like being critical but offering no solutions. You're just kind of complaining.
Yeah, it really shouldn't be a place to complain, right? It's about constructive criticism, right? What might be a constructive criticism that you might put in there in general? Don't pick on anybody right now.
It'd be nice if we had study guides or.
Okay, yeah, you could do those types of things, right? What else? If you find yourself wanting to write something very negative about a faculty member, do not do that in the teaching evaluation. If you really have a real complaint, what do you need to do? What do you need to do if you really think a faculty member is doing something wrong? You need to go to somebody of authority. Right, you can go to the Dean of Students. Anybody know who that is? Serena Cantrell. Yeah, you could go to the Dean of Students. Who else can you go to?
The person headed up before me.
Okay, yeah, so we call them school directors, right? So if you were in a class and you felt like, you know, what this instructor is doing is not aligning with the mission of the institution or you know, fair or whatever, go talk to the school director. That's perfectly legitimate, okay? And it will probably get you further than writing it down in the course evaluation. And here's why. All right, so you're one person, let's say you're in a Gen Chem class, and you felt like something was wrong. You're one person that puts that in there, and everybody else is putting something else. It gets diluted, right? But if you go and talk to the school director, you have a forum, right? You have a way of expressing that complaint or concern, okay? So putting those types of things in your course evaluation isn't going to be highly effective, I can tell you that. But what is going to be highly effective is when I sit down and I look at my course evaluations when I'm teaching something like organic, and I start to see, oh, well, I'll just give you the real example. So I used to teach over in Walker, in Big Reuben, that holds 180 people. And when I first started teaching, I would sit back here and I would do this, and I would talk and I would say what was on the slides. And I noticed the first couple of times that I taught, I got all of these comments about I needed to be more interactive, I needed to ask more questions. So you have that, I mean, I walk around, I talk to y'all, we interact, we do things, right? That all came from the fact that my students taught me that I needed to do something better. I made a change, right? It wasn't because of what you wrote or what you wrote, it was what you all wrote, and I noticed that there was a common theme of I needed to be more interactive and more, less this, right? Whatever you want to call that, right? So, also, you all get videos posted to my YouTube channel because of what students gave me as feedback. Students were saying, you know, you're covering a lot of material, which was just how organic chemistry is. You got to cover a lot of material. People were saying, you give us the slides, but yet I don't really have that connected to what you were saying. And so I thought, I'll just record the lectures and I'll put them up. If somebody misses class, they've got access to it. If they couldn't write something down, you know, they could go back and listen and get it later. That came from student feedback, okay? So again, you all are benefiting. Some of you probably had to miss class one day and you might have went and listened to the video, right, that I recorded. Maybe you did, maybe you didn't, but it was available to you, right? All of that came from student feedback. So I want you all to know that faculty members, the vast majority of faculty members, usually in January, because we don't want to ruin our Christmas, right? But usually in January, we sit down before classes start and we do go through the summaries of what you wrote. We typically pay less attention to the numbers and pay more attention to what you wrote, okay? And another thing to keep in mind, if you want to keep it truly anonymous, make sure when you're typing things out, do not put your name at the end. I have students that do that sometimes, you know, and so just kind of keep that in mind. Does anybody have any questions about course evaluations? I know it's tedious. I know it comes at the end of the semester. I know it comes at a time when you're trying to study, and it does end at the end of the semester, but it is your opportunity to have your say. And take that seriously. It is part of your opportunity to shape the future of how students sitting where you are now will have a better experience, and you are benefiting from the things that other people have said as well. So pay it forward. Okay? All right. We will not be meeting next week. It will be Thanksgiving. I want you all to have a good Thanksgiving break. One piece of advice: Thanksgiving break, we can lose a lot of momentum. So while you enjoy your break, do spend a little bit of time, because remember, the turnaround before finals is very, very quick. So keep that in mind. Yes? We do. We have one more class meeting in here. That will be our final class. So go ahead and put your name, ID number on your note card. Leave it up here. And I will see you week after next. Enjoy your Thanksgiving. Be safe. Stay healthy.